Hello class, welcome back for the second part of the Multilinear Regression 1 video. Now we are actually going to start talking about multilinear regression. So let's think about this kind of logically. Real problems in the real world usually don't involve one, but in actuality many predictor variables. And so that is some important response variable y may be related to some m number of predictors. So the point of chapter 8 in our textbook is to generalize our simple linear regression analysis of chapter 7, which we have based on an approximate relationship of y being about equal to beta naught plus beta 1x, and generalize that to the more complicated multilinear regression context where y is going to be approximately equal to beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 all the way to some beta m xm. And as it turns out, a lot of the things that we learned in chapter 7 for regression analysis can be generalized to the more complicated case. So let's start by taking a look at our real estate example. So in our real estate data, we're now not going to just be focusing on size as it relates to selling price, but now we're going to be looking at both size and condition. So you may be wondering, what is this condition variable? And what occurred is usually, well, at least not usually, but I'll say in this case, the houses that were observed were ranked on a scale from 1 to 10, 1 being the worst and 10 being the best, and gave each of the houses a condition value, in addition to recording the size of the house and its selling price. And so we can look at the full data set here in slide 144, and so we can see that our approximate equation in this case, since we are examining two variables, predictor variables that is that y is going to be approximately equal to beta naught plus beta 1 x1 plus beta 2 x2, where we can see our 1 subscripts are going to be a representation for size, x1 is size, and x2, and whenever we use the subscript 2, will be to represent our condition predictor. And so the first step in a multilinear regression analysis is to fit a equation. And our equation is going to be a nice extension of our simple linear regression. And so instead of having mu hat of y given x equal to beta naught hat plus beta 1, or beta 1 hat x, we now have mu hat of y given x1, x2, all the way to xm, which is equal to beta naught hat plus beta 1 hat x1 plus beta 2 hat x2 plus dot 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 all the way to beta m hat xm for our n data cases, which are x1, x2, all the way to xm, and of course our observed response y. And so just as is in simple linear regression, we do use that principle of least squares. And so we can also then have our observed, what eventually would become our sum of squares error, where we have this observation of the difference between our actual responses versus our predicted responses. Now, unfortunately for you guys, well, both fortunately and fortunately, a lot of stuff that we would like to examine in Chapter 8, I can't ask you to do by hand because it requires a level of calculus that is beyond the scope of this course. So you're going to hear me refer to this a lot, where we will be examining values, but we can't calculate them. We'll have to get them from JUMP. So for us, our coefficients are beta naught hat, beta 1 hat, beta 2 hat, all the way to beta m hat. Our least squares coefficients, we aren't going to be able to calculate them directly. We have to only observe them through JUMP. It is very important to understand that a lot of our simple linear regression knowledge does extend, but the formulas we used do not. So to kind of get an idea of how this looks geometrically, we are going to focus on the case where we have two predictors. So before, what happened in the simple linear regression case, you had this XY plane and a bunch of our responses in a scatter plot, and then we fit our line of least squares, and we kind of had to like metaphorically jiggle that line so that it created the least amount of difference between our predicted line and our actual values. Well, thinking about it now, we have to extend it with our two predictors to a three-dimensional model. So instead of a plane, we now have a cube, and we can think of it as you have this cube which represents our space, and instead of having two-dimensional dots, we now have these floating orbs that are our responses. And so instead of trying to fit a single line, we're now trying to fit a plane, or if you want to think about it, a piece of paper. And the same concept as we used before, we're going to kind of try to jiggle this paper so that it is as close as possible to our floating orbs so that the distance between the orbs and our piece of paper are as minimized as possible, or least. And so if we take a look at our real estate example, we can see that we have to have a jump report, and from this jump report we are given our parameter estimates, and with these parameter estimates we can have our least square coefficients. So in this case, our beta naught hat is going to be equal to 9.78, our beta 1 hat is equal to 1.87, and our beta 2 hat is going to be 1.28. So this means our least squares equation in our real estate example is going to be mu hat of y given x1, x2, which is equal to 9.78 plus 1.87 x1 plus 1.28x2. Notice that in addition to our parameter estimates, we are given the standard error for each term, a t-ratio, and a p-value. We'll talk about the standard error measurements in this course, well, we'll talk about all of it in this course, but in this lecture, we will address the standard error measurements, but we will focus on the t-ratio and the probability columns in later lectures. Essentially, though, this part is those individual t-tests that I mentioned earlier. So one thing you may have noticed looking at our parameter estimates is that the beta naught hat and beta 1 hat for our multilinear regression model was not the same values as it was for simple linear regression. And so we just need to be aware that the coefficients beta hat and multilinear regression are rates of change of y with respect to one predictor, assuming that all other predictors are held fixed. And so that is, it's the change in response that accompanies a unit increase in the predictor if all other predictors are held fixed. So what happens when we're using a simple linear regression situation? We have one x, one y, one predictor to try to explain our response. In that case, we assume or we ignore that any other predictors even exist. In multilinear regression, we are acknowledging that there are multiple predictors. And what each of those estimates are doing is they are still representing a rate of change, but we have to hold all other predictors at a fixed state. So if we're thinking in terms of the real estate example, it would be comparing the increase in price as we increase our size while holding that condition at, say, a level 5. And seeing, while we look at all houses that have the same condition level, how does the price of the house change in accordance to size? So as you will definitely be asked to define your beta slope estimates, we can say this formally that beta j hat is an estimate of change in our mean response y that accompanies a unit increase in the jth predictor xi if all other predictors are held fixed. So using our real estate example, beta 1 hat is equal to 1.87, and this indicates an 18.70. Wow, sorry, trying to speak here. A beta 1 hat equals 1.87 indicates an $18.77 feet squared increase in price, holding the home condition fixed. And beta 2 hat equal to 1.28 indicates that homes for a fixed size, an increase in the home condition number by 1 is accompanied by a $1,280 increase in price. And a nice way to see this in a two-dimensional sense is where we have our size of our house held at a fixed state. In this case, we have it at x1 equals 0. And so basically we've made just, well, in this case, if we're going to have our size at 0, I guess we would have to consider that as a plot of land without a house being built on it. And so we're holding that condition of x1 equals 0 fixed and seeing the increase in our response as we increase our size condition. Although now that I'm looking at this, yeah, no, that holds still. But we can see that each of these lines have our slope and then our y-intercepts increase. So take a look at this. There is a lot of information to unpack in this chart, and I certainly didn't cover everything. So moving on to our next piece of information would be to talk about how do we measure the goodness of fit of our least squares equation. And so in an extension of our simple linear regression, we are still going to use that r squared value or the coefficient of determination. In fact, the formula for this is the same, but we won't be able to calculate our sum of squares error by hand. However, the total sum of squares, which is still equivalent to the summation of each individual response minus the mean of our response, quantity squared, it doesn't actually depend on the model we use. So regardless of whether we have one predictor, two predictors, or 50 predictors, our total sum of squares is actually going to remain the same. But like I said, the issue does come along with trying to calculate our sum of squares error. We can no longer calculate that by hand, so we will have to get that from GEM. And for our sum of squares regression, that is still related to our sum of squares error and total sum of squares as it was before. So we will equally not be able to calculate that by hand without being first given the sum of squares error. But the calculation of r squared is still the same as SSR over TSS, or my preferred 1 minus SSE over TSS. And now we will notice it and define it as the fraction of raw variation in y accounted for by the fitted equation, or we can say the fraction of raw variation of y accounted for by our predictor variables x1, x2, all the way to xm. And so as we can see, the formulas above look exactly like they did in SLR. What did change is our interpretation of the mu hat of y given xi1, xi2, all the way to xim. And so for multilinear regression, each predicted value is obtained by plugging in the values of all m predictors for that observation into our fitted equation. So that is mu hat of y given x1, x2 all the way to xm is equivalent to beta naught hat plus beta 1 hat x1 plus beta 2 hat x2 plus dot 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 plus beta m hat xm. And as I've stated many times, and I will have to say many times, these calculations are a job for jump. The only exception is we will be able to do some of it when we have a very small data set, like our small fake data set. And so looking at our real estate example, still examining this idea of our coefficient of determination, let me remind you that in our real estate example, our response is y, which is our price, x1, our predictor is size, and then our second predictor, x2, is condition. So we may recall that for our simple linear regression on x1, we produced an r-squared value of 0.88, but on multilinear regression on both x1 and x2, we produced an r-squared value of 0.99. And again, comes straight from jump. And so this is something that we do need to consider. So you've noticed that obviously there was an increase in R squared from the SLR model to the MLR model. This is not surprising. Anytime we add a predictor variable, we are always going to see an increase in R squared. So really what we actually are going to really want to pay more attention to is whether or not that increase was large enough to justify the extra complication involved in using an additional predictor. And so what I mean by that is for the SLR model, our R squared was 0.88. If we had added in an additional predictor, say album sales of Taylor Swift's latest model, logically, that doesn't have much to do with the selling prices of houses unless it's Taylor Swift's house. But the point is, that really isn't going to help improve the model. It just exists. Well, with the way that R squared is calculated, anytime you add any sort of predictor in, it's going to increase the R squared value. The question is, did it increase it enough? So we might get an R squared value if we added in Taylor Swift's album sales to be 0.89. And so at that point, we ask ourselves, okay, yes, there's an increase, but is there enough of an increase that it's worth keeping track of Taylor Swift's albums? Well, probably not. It's much easier just to keep it simple. In statistics, we like to have as simple a model as possible. Why? Well, simple models are easy to use. They are also easy to explain. Now, one little thing to talk about still with our real estate example. If we were to go through and calculate the simple linear regression model using only the predictor of condition, we would get an R squared value of 0.14. Now, at this point, you know that R squared equal to 0.14 is not that great of an R squared value. You would look at it and kind of question whether you'd want to even use that predictor at all. And at the very minimal, you can see that size is definitely a better predictor of selling price than condition. Well, the thing about the multilinear regression model is it's not simply a sum of the R squared values from two simple linear regression models, meaning that 0.88 and that 0.14 are not equivalent to that new multilinear regression R squared value of 0.99. And the reason for that is that there's going to be a correlation that exists oftentimes between predictor variables. And if you think about this, if you have a huge mansion that's, $1 million mansion, chances are if you can afford a house that cost $1 million, chances are you're going to also be able to afford the upkeep of it. And so there is this correlation between the size of the house and its general condition. And that is something that we do have to just be simply aware of. And so in regression analysis 1, we noted that in our simple linear regression that R squared can be thought of as the squared correlation between our single predictor X and Y. In our more complicated multilinear linear regression contents, there's now several x's, but R squared is still considered a squared correlation, but it isn't necessarily as natural one. It is the sample correlation between our actual responses and our predicted response values, quantity squared, and still boils down to our R squared. And so for the sake of interest, we can do some calculations by hand using our small fake data set. So notice that I've added in a new predictor x2 with the values of 0, 0, 1, 1, and 1. So now going through, we can now calculate a new predicted response and new SSE and a new R squared. And so we're given that with our two predictors, we now have a new least squares equation of mu hat of y given x1, x2, which is equal to 0.8 minus 1.8 x1 plus 2 x2. And so now using that equation, we can find our predicted y's because our y column is our actual y's and these are our predicted. So by plugging in 0.8 minus 1.8 times negative 2 plus 2 times 0, we will get 4.4. And if we go through plugging into our equation, we will get 2.6, 2.8, 1, and negative 0.8. In our next column, we are asked to subtract our actual y's minus our predicted. And so from here, 4 minus 4.4 would be negative 0.4. 3 minus 2.6 would be positive 0.4. 3 minus 2.8 is 0.2. 1 minus 1 is 0. And negative 1 minus negative 0.8 is negative 0.2. Notice if we add up this column, we get 0. If we have done things correctly, this column should be approximately 0. The only reason it wouldn't be 0 is if you had to do some rounding. And next, we can still continue on our journey to calculate our sum of squares error by squaring the difference between our actual and predicted values. So negative 0.4 squared is 0.16. Same when it's positive 0.4. 0.2 squared is 0.04. And 0 squared is 0. If we take the sum of this column, we will get 0.4, which is going to be our sum of squares error. And so now using this, we can actually calculate our R squared. We may recall R squared is equal to 1 minus SSE over TSS. We just calculated our SSE as 0.4. And we remember that TSS isn't dependent on our equation. It is the summation of our individual y's minus the average y quantity squared. And so we actually calculated this in our SLR1 notes. And this value is 16. So doing our math, we will now have an R squared value of 0.975, which on the surface looks pretty good. So now let's take a look more at our point estimates of our parameters as we've continued on in this lecture. So the most convenient or common model supporting inference making in MLR is the normal multilinear regression model that we've already introduced before. And this can be described in several words. In words, the normal multilinear regression model is the average of y is linear in each of m predictor values, x1, x2, all the way to xm. So that is mu of y given x1, x2, all the way to xm equals beta naught plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta m xm for a given set of predictors, x1, x2, all the way to xm, and y is normally distributed with standard deviation sigma that does not depend upon the values of x1, x2, all the way to xm. And so if we want to have an understanding of this pictorially, again, we do have to consider it in a three-dimensional situation where we have our y-axis, our two axes for our conditions, conditions, predictors, x1 and x2, and each of our responses we can see are normally distributed with a variance of sigma squared or a standard deviation of sigma. So in symbols, as we are aware, our multilinear regression model is really going to be y equals mu of y given x1, x2, all the way to xm plus epsilon. Now, by now you've heard me repeat what mu of y given x1, x2, all the way to xm is, so I will try to repeat that as little as often. But what is going to be interest to you is what is this epsilon? And this epsilon is that same error term that you are familiar with. It allows for the observed response to deviate from the relationship between x and average y. And so our little epsilon represents the difference between what is observed and the average response for that x1, x2, all the way to xm. And it is, of course, assumed to be normally distributed with mean 0 and standard deviation sigma. That does not depend on x1, x2, all the way to xm. And so what we do have to understand is that when we are calculating our model, we do what is the average, and we assume things are normally distributed. So most things are going to be near the average, but it's not going to be exact. So we have this error term to make it understood that our predictions aren't exact, but they should be close. So if we are considering our single number estimates of our parameters of the normal multilinear regression, they are going to be pretty much the same as they were in simple linear regressions. The parameters beta naught, beta 1, beta 2, beta m will be estimated using our least squared coefficients, beta naught hat, beta 1 hat, beta 2 hat, all the way to beta m hat. Again, these must come from jump. And our sigma, that population standard deviation, is going to have to be estimated using the sample standard deviation of S of y given x1, x2, all the way to xm, or in other words, the root mean squared error, which we learned about earlier. I do want to emphasize that this sample standard deviation is not the one that we discussed in chapter 1.5, nor is it the same as the simple linear regression estimate that we talked about in our SLR2 notes. This is one that is specific to the multilinear regression context. And so now at this point we can start taking a look at this in an example format. So in our real estate example, where our response is price and our two predictors are size and conditions, our simple linear regression model on size produced a sample standard deviation of 3.53. And for the multilinear regression on our two conditions, we produced a sample standard deviation of 1.08. And again, this comes directly from JUMP. Specifically, I got this on slide 156. And so we note that the estimated standard deviation of price for any fixed combination of size and condition is substantially smaller than the estimated standard deviation of price for any fixed size. Again, so the more predictors we add, the less variation we should see, because the more variation that has been explained by our predictors. And so this finally leads us to the final focus of this lecture, and that is making confidence and prediction intervals in multilinear regression. So to start with, we're going to be making confidence limits for sigma and confidence limits for any predictor. And so for our confidence limits for our standard deviation, it is going to be based on the chi-square distribution with degrees of freedom n minus our number of predictors plus 1 distribution. So when it was a simple linear regression, it would have been the chi-square distribution with n minus 2. And we will use the interval of the root mean squared error multiplied by the square root of n minus the quantity n plus 1 over the statistic of chi squared at alpha over 2 to the upper limit of the root mean squared error multiplied by the square root of the degrees of freedom that exist for the sum of squares error over the chi-squared value at 1 minus alpha over 2. And for our confidence limits for any predictor, beta j, we'll still use the same formula that you're familiar with, where beta j hat is plus or minus t alpha over 2 multiplied by the standard error of beta j hat. We will still use the t distribution. What does change is our degrees of freedom, which are going to be n minus the quantity m plus 1. As I've stated many times, you cannot get your parameter estimates through hand calculations. You are going to have to get them through JUMP, and you will also have to do the same thing for your standard error. It must be given to you so that you can calculate your confidence limit. You will be able to, of course, look up your critical value on the t-table. So let's take a look at an example of this. And so using our real estate example with our price being our response and size and condition being our predictors, let us create a 95% confidence limit for the standard deviation of selling price for homes of any fixed size and condition. We're familiar with the formula. Now what is left to us is to plug in and look up those critical values. And so we know the root mean squared error in the real estate example is 1.08. We established that on 2 slides previously. And we will take the square root. Our sample size is 10. We have 2 predictors. And I will now copy the same on the other side. And so now what is up to us is to look up our chi-squared critical values. So I'm going to go ahead and I am going to pull up the chi-squared table. But actually, you know what? Before we do that, I want to do one other thing first, and that is to establish our alpha level and our degrees of freedom. And so in order to calculate our chi-squared critical values, we do need to know our degrees of freedom, which in this case is that 10 minus the quantity of 2 plus 1. Well, 2 plus 1 is 3. 10 minus 3 is 7. And now we need to get our alpha over 2 and 1 minus alpha over 2 values. So we were given that this is a 95% confidence limit. And so that can tell us that our alpha value is 0.05. So that means alpha over 2 is 0.025. And that means our 1 minus alpha over 2 is going to be 0.975. And so this is the information that we need in order to get our critical values. Okay, so once again, we've established that our degrees of freedom is 7 and that we needed alpha over 2, which is 0.025, and 1 minus, which is 0.975. So that means our critical values of interest are 16.013 and 1.690. So now at this point, we can go back to our slides, plug in. And so now that we've plugged in, we can use our calculators to get our confidence interval, which would be 0.71 to 2.2. And again, this is per $1,000. And so we can now make our proper interpretation and say that we are 95% confident that the standard deviation in prices is between 710 and $2,200 at a fixed size and condition. And so notice I underlined prices, size, and conditions. That was our response and our two predictors. So as you go through this course or in the future, if you have to interpret a confidence interval for standard deviation, you can use this general statement and sub in for your different predictors and response. Moving right along, we can also calculate a confidence interval for our two predictors. So as you can see, we have our jump report that gives us our least square coefficients. And our column where it says standard error, that is the standard error of our estimates. And so what this means for us is that for size, we can create the confidence interval of 1.87 plus or minus our T alpha over 2. If we use our T table with degrees of freedom of 7, we would get a critical value of 2.365. And we can multiply this by our standard error of beta 1 hat, which we can see is going to be about 0.076, which we could simplify this to be 1.87 plus or minus 0.18, which then would simplify to be 1.69 to 2.05. Next, we can construct a 95% confidence limit for condition using the exact same process. So this would be become 1.28 plus or minus 2.365 multiplied by our standard error, of beta 2 hat, which would be 0.144. And so this would become 1.28 plus or minus 0.34, or our confidence limit would become 0.936 to 1.6195933. You may be wondering, where did this last part of the jump report come from? Well, one option is that you could look at your jump handout, but just to let you know, once you get your fit model report, if you select that red triangle and then select regression reports, you will see an option that says show all confidence intervals. If you select that option, then these confidence intervals will pop up for you. If you want to change the alpha level from 0.05, you will have to do that when you construct the model. And so if we want to do this for our small fake data set, we absolutely can. And so let's take a moment and construct a 95% confidence limit for sigma, beta 1, and beta 2. And so for sigma, our confidence interval would be, well, let's see, our root mean squared error for our small fake data set was 0.4472. And if I recall, so that our sample size was 5. We had 2 predictors, so that would be minus the quantity of 2 plus 1. And we'll need to calculate our critical values in a moment. Copy this over, so this becomes, again, 0.4472 multiplied by the square root of 5 minus the quantity of 2 plus 1. So looking up our confidence levels, we know 5 minus the quantity of 2 plus 1. 2 plus 1 is 3. 5 minus 3 is 2. So our degrees of freedom for this problem is going to be 2. And we are still working with that same confidence level of alpha equals 0.05. So if we try to take a look for our chi-square distribution table, degrees of freedom 2, but since our confidence levels are the same, we can still look at those same columns. And so our critical values in this case are going to be 0.051 and 7.378. And so if we simplify this, we will get a confidence limit that goes from 0.233 to 2.800. And now we can move on to constructing our confidence limits for our predictors. So for beta 1, this would begin as negative 1.8 plus or minus, and I'll tell you the T alpha over 2 value is going to be 4.3027, and we were given that the standard error is 0.283. So this is going to give us a confidence limit of negative 3.018 to negative 0.582. And then for beta 2, this would be 2 plus or minus 4.3027 multiplied by the given standard error of 0.816 to give us a confidence limit of negative 1.511 to positive 5.511. So excellent. And so now that we've taken a look at this, we can now focus on making inferences for responses instead of for model parameters. So let us consider confidence limits for the mean response and prediction limits for our new response. So suppose that we have a set of values for our predictor variables x1, x2, all the way to xm is of interest, and that for these values of the predictor, one has computed a predicted value of mu hat of y given x1, x2, all the way to xm. And so in that case, our confidence limit for mu of y given x1, x2, all the way to xm is going to be mu hat of y given x1, x2, all the way to xm, plus or minus t alpha over 2 multiplied by the standard error of mu hat of y given x1, x2, all the way to xm. We do use the t distribution and the same degrees of freedom as we used previously. That is n minus 1 multiplied by the quantity of m plus 1. We of course, do have to get our mu hat of y given x1, x2, all the way to xm, and our standard error measurements do need to come from the jump report. And then we can also calculate a prediction limit for a new predicted response value. The formula for this will be mu hat of y given x1, x2, all the way to xm, plus or minus t alpha over 2 multiplied by our standard error of our prediction. Once again, this will follow the t distribution with degrees of freedom n minus the quantity of m plus 1. We can get the standard error of our prediction from jump. We could also calculate it by hand if we so desired. The standard error of the predicted value is equivalent to the square root of our MSE plus the standard error of our predicted, standard error of our prediction squared. But you do need to get the MSE and that standard error value from your jump report. And so just to have an understanding of what these look like in JUMP. So once you get the fit model report in JUMP and you want to get the necessary outputted values, you can do this by going to the red triangle and selecting Save Columns. Your mu hat of y given x1, x2, all the way to xm is written as predicted values. Your standard error of mu hat of y given x1, x2, all the way to xm is written as the standard error of predicted. And then your standard error of predicted is written as the standard error of the individual. Also, if you want to skip that step and just go straight to being given your confidence and prediction limits, you can do that. One of the save columns options is the mean confidence interval. That will give you what you are thinking of when we are constructing a confidence interval. And when it says individual confidence interval, that's what you think of when you hear a prediction interval. So this is the way that you're honestly probably going to have to go about calculating these confidence intervals for your homework, unless given very specific jump output. So taking a look at an example using our real estate data, where our price is our response and size and condition are predictors, let us consider a 2,000 foot squared home with a condition number 9. And note that the third home in the data set does have these characteristics. So after saving our jump model report, we can get our predicted values, our standard errors, our confidence intervals, and prediction intervals, and we can obtain the following values. I do have the jump report included on slide 172. And so as I write these values, they're not coming out of thin air. So our predicted value would be 58.7042. Our standard error of our prediction would be 0.6375, and the standard error for our predicted interval would be 1.2546. And so our 95% confidence limit for mean price of such homes would be $57,196 to $60,212. And our predicted interval would be 55,736 to 61,672. And again, you should get all of this information in JUMP And so let's go ahead and take a moment and just do that now. I do know that it is on the jump video, so you are welcome to skip this part, but sometimes it is helpful to do it together now. So taking a look at our real estate data, and you can get this off eCampus. If we go to Analyze, Fit Model, we can begin constructing our Fit Model report. So selling price is our response, size and condition are our responses. Now, in the event that you are asked to construct something other than 95% confidence, you can do that now by selecting this red triangle, sorry, clicking the right one, the one next to model specification. You have the option to set the alpha level. The default is at the 5% level, but we can change it if needed. Pretty much all the examples I gave you in class are at the 5% level, so we haven't really had to change it, but you definitely are able to. Also, if we need to predict something that's not already given in this table, we can do that at this point by adding in. So for example, if we wanted to see what would happen if we have a house of size, we'll say 18, and home condition 3, we can use this while we are constructing our fit model report, and we can get those predicted values. So let's demonstrate that right now. So by going Analyze Fit Model, once again, selling price goes to our response, size and condition are our predictors. So now we can go ahead and select Run. I'm going to scroll down for a moment, and you can see we have our parameter estimates, our ANOVA table, and our summary of fit. Earlier in this lecture, on slide 166, I talked about how you can get those confidence limits off the parameter estimates. I will show you how to do that right now since I did talk about it. Red triangle, regression reports, show all confidence intervals. And there it pops up. And so now the main part we were looking at is how can we get all those predicted values, the mu hat of y given x1, x2, the standard error measurements. Well, once again, we're going to select the red triangle, save columns, predicted values. That's going to give us the mu hat of y given x1, x2. We are also interested in getting our standard error of our predicted and the standard error of the individual. And because we may be feeling a little bit lazy, let's go ahead and take a look at our confidence interval and our prediction interval. And so if I minimize the screen and go back to our original table, you can see that we now have everything we would have needed to calculate by hand given to us, including that extra line where I said, okay, maybe we're curious about a house of size 18 and at condition 3, we can get the predicted values, the predicted standard errors, and our confidence intervals for these measurements, even though the selling price is unknown. And this is an important skill because I will ask you to do this in your homework. All right, so to finish up this lecture, we have one last slide, and that is to use that small fake data set to create a confidence interval and prediction interval. What I'm going to do is I'm going to give you just the final answers, and I'm going to let you go ahead and calculate this on your own so you can get that extra practice. If you get stuck, send me an email, but for this, I'm just going to give you the final answers. So for the confidence interval for our small fake data set, it's going to go from 2.91 to 5.89. And our prediction interval will be from 1.966 to 6.834. Again, give this a try on your own, and if you have any questions, please shoot me an email. This brings us to the end of this lecture. If you need anything, as I've repeated a couple times already, send me an email. Have a great night.